and welcome back for part 2. We'll start off with number 22, the true-false questions. So our first one, if W is a subspace of Rn, V is in W and W perp, then V must be the zero vector. So let's think about that for a second. If V is in W perp, then by definition, V dotted with any W that's in W perp, or any W that's in big W, the subspace, is going to be 0. V being orthogonal to the subspace W means that V is orthogonal to every vector in W. But that includes V. So because V is in W. So V dotted with V is 0. But that means that the norm of V is 0, which means V must be the zero vector. The only vector with norm 0 is the zero vector. So this statement is true. All right, let's look at B. In the orthogonal decomposition theorem, each term in Formula 2 for Y perp is itself an orthogonal projection of Y onto a subspace of W. Okay, so in analyzing this statement, we need to look at that Formula 2 and look at each term. So basically this is asking, is this an orthogonal projection of Y onto a subspace of W? And the answer is yes, it is. Because this expression, y dot u1 over u1 dot u1 dotted with u1, this is the projection of Y onto the subspace spanned by the vector u1 by itself. It's just like what we did in 18 here when we projected Y onto the subspace spanned by u1. See, this is exactly one term of that Formula 2. So this statement is also true. Statement C, if Y equals Z1 plus Z2, where Z1 is in W and Z2 is in W perp, then Z1 is the orthogonal projection of Y hat onto W. So I want to draw your attention to Theorem 8, which says that if W is a subspace in Rn, then each vector Y in Rn can be written uniquely in the form Y equals Y hat plus Z, where Y hat is in W and Z is in W perp, and in fact Y hat equals the orthogonal projection of Y onto W. So it says all of this in Theorem 8. So now let's compare that with the statement above. Well, the key word in Theorem 8 is that can be written uniquely. There is only one way to write Y as Y hat plus, as a sum of two vectors where the first one is in W and the second one is in W perp. So if we have such a sum, such a linear combination, so we have that Y hat equals Z1 plus Z2, and it equals Y hat plus Z, where Y hat is the projection. Since it's unique, that means that these two are the same. So this statement is true again. Now let's move on to D and E. D says the best approximation of Y by elements of a subspace of W is Y minus the projection of Y onto W. So let's look at this picture. So if this is Y and this is W, then Y minus the projection of Y onto W is actually this vector, which isn't even in W necessarily. This length is the distance between y and w, but this vector itself might not even be in w. So we can't approximate y using this vector if this vector isn't even in w. So this statement, just from the picture, is automatically false. However, we can see it again from the best approximation theorem, which says that y hat is the closest point in y to w. This part is y hat. So if y hat is already the best approximation, then y minus y hat is not going to be a better approximation. So the true statement is that the projection of y onto w is the best approximation, not y minus that vector. Letter E. If an n by p matrix U has orthonormal columns, then UU transpose X equals X for all X in Rn. Is this statement true or false? Well, if we look at Theorem 10 says that UU transpose X equals the projection of X onto W. So this statement would say that the projection of X onto W, that's this part, always equals X. Is that always true? Well, let's go back to what we did on question 18. Does U transpose Y, negative 2, 6, equal Y, 7, 9? No. So this statement is false because it's not always true. All right, those were the true or false. I think I'll make a separate video for the very last question, number 24. So let me close this out and I will see you soon.